It's a great pleasure to have Viktor Ginzburg with us today. The title of his talk is Invariant Sets and Hyperbolic Periodic Orbits of the Reeb flows.
All right, thank you all for having me here. So I'm going to, here is the a table of contents. I'm going to talk about a peculiar and not particularly new phenomenon. Whenever you have a Hamiltonian system and whatever that means, a Hamiltonian system, and it has a hyperbolic periodic orbit or several hyperbolic periodic orbits, this usually just by itself or oftentimes implies some interesting dynamic. And actually, it's slightly more general. Rather than having a hyperbolic orbit, it might be enough to have a locally maximal periodic orbit, and locally maximal means isolated as an invariant set. So, for instance, a hyperbolic orbit is locally maximal, but it does not have to be. A monkey saddle is also locally maximal, and there are other examples. So the most prominent phenomenon or manifestation of this phenomenon is, of course, homoclinic intersection. When you have a hyperbolic periodic orbit with transverse homoclinic intersections, you get a horseshoe, you get positive entropy, you get interesting dynamics, and actually, in the Hamiltonian case, the existence of transverse homoclinic intersections once you have a hyperbolic orbit is a C1 generic condition. A slightly less known manifestation of a very different type is a lower bound on the spectral norm. Whenever you have a Hamiltonian diffeomorphism with sufficiently many hyperbolic periodic orbits, there is a lower bound on the spectral norm of the iterates of that Hamiltonian diffeomorphism. And this is, again, a C infinity generic condition. So these are two examples where somehow the existence of a hyperbolic or locally maximal periodic orbit has interesting dynamical implications. And this is not what we are going to talk about. So we are interested here in two other manifestations of the same thing. One is a multiplicity type question. Whenever you have a hyperbolic fixed point of a Hamiltonian diffeomorphism of a projective space, that diffeomorphism necessarily has infinitely many periodic points. So the existence of just one hyperbolic fixed point implies that there are infinitely many periodic orbits. There are, of course, nowadays much more advanced results along these lines, and this is in turn a variant of Frank's theorem for area-preserving diffeomorphisms of the sphere, and by now, there are generalizations by Yegor for the projective space, namely if a Hamiltonian diffeomorphism of a projective space has more than necessary fixed points, then the number of periodic orbits is infinite. So this is the first result I want to look at. And the second result is closely related. Namely, in the previous theorem, one can replace a hyperbolic fixed point by a locally maximal fixed point. And again, to repeat, the locally maximal fixed point means it's isolated as an invariant set. The corollary, or another way to look at the same thing, is that a Hamiltonian pseudo-rotation of CPN has no locally maximal fixed points. In other words, when you have a Hamiltonian pseudo-rotation, a Hamiltonian diffeomorphism of CPN with exactly n+1 fixed points, no fixed point is locally maximal, no fixed point is isolated. There will always be invariant sets in an arbitrarily small neighborhood. For S2, this is a theorem of Calvez-Yoccoz and Franks. And so the main theme of this talk, of this project, is to look at the analogues of these two results, these two closely related results for Reeb flows on the sphere. Are there any questions about what we are trying to do here and sort of what the theme of the talk of the project is? Guys, anyone? Questions? Yes, sir?
A sphere is just because it's the basic example, right? Where you have the Hamiltonian story and you want the context version of it, and a sphere is the first example to try.
So, yes, but in essence, this is the answer. Once you move, I'm going to comment a little bit on that later, but once you move to higher dimensions, if you want to prove something about Reeb flows, you really need to make assumptions. It's kind of results become very specific to manifolds. And here I tend to think of the sphere as an analog of the projective space. Kind of.
Thank you.
Other questions? All right, then let's see the results. So we are mainly interested in the standard contact sphere. And I want to think of it as a boundary of a star-shaped domain in R2n. So here is a notation. We are going to look at the collection of closed Reeb orbits, and these are simple or uniterated orbits. In addition to what we said, usually in higher dimensions, you need to make additional assumptions if you want to prove something. You cannot just prove things, and I'll get back to this, about an arbitrary Reeb flow on the standard contact sphere. And most common type of assumptions is dynamical convexity. It's introduced by Hopper, Wysotsky, and Zender in the late 90s. And literally it means that the Conley-Zender index of every orbit is bounded from below by n+1 when we are looking at the 2n-1 dimensional sphere. For instance, for the 3-dimensional sphere, it should be 3. But sometimes people use weaker versions of dynamical convexity, but I'll get back to it. In essentially all results in higher dimensions, some kind of dynamical or some kind of index assumption is there. Otherwise, you just cannot prove a thing. And dynamical convexity in this pretty strong form is a consequence of convexity. The converse is not true. By now, the first result of this type is, or the first example of this type is Kaides and Edmar, and then there are constructions by Christopher Gardner and Hind, and then got Ramos and Zhang, and so by now this is a well-understood question. So many parts of what we are going to talk about, though, or some parts at least, work for more general Liouville domains. So there will be pieces here and there that hold in general. So the first result we will talk about is multiplicity. There are a couple of extra ingredients I need here to state the result. The first one is the mean index. This is just the index of the iterates divided by the order of iteration, and then the limit is taken. And then I'll need the algebraic multiplicity. So assume that we have a Reeb flow on this standard contact sphere with a hyperbolic Reeb orbit Z, and it satisfies a very mild version of dynamical convexity condition. So this is a lower bound on the index. Then there are infinitely many simple periodic orbits. So that's exactly an analog of the result for CPN you get for the Reeb flow. One useful point here is that I'm imposing no non-degeneracy condition. Here, the flow can be completely degenerate, except, of course, this hyperbolic simple orbit is non-degenerate. So this is the first result. And the second result is about invariant sets. So again, I have a standard contact sphere, and now I need to assume more in general. I have dynamical convexity, and I want to assume that the flow is non-degenerate. And let's also assume that it is a Reeb pseudo-rotation. And in this case, I simply need it to have finitely many simple orbits. So this is kind of as loose definition of a pseudo-rotation as it can be. Then every closed Reeb orbit is locally, sorry, the other way around. Then there are no locally maximal closed Reeb orbits. So none of them is isolated as an invariant set. The neighborhood of each of them will contain an arbitrarily small neighborhood of any orbit will contain some other invariant set. So this is the Reeb analog or a Reeb analog of the second result. So this is, one should think of it as a non-degenerate version of the Calvez-Yoccoz theorem for Reeb flows. We almost have like the second theorem implying the first theorem because a hyperbolic orbit is necessarily locally maximal. So if I turn the other theorem around, it will say that whenever I have a locally maximal periodic orbit, the total number of periodic orbits is infinite. So it becomes a statement exactly along the lines of the first theorem, except the conditions of the second theorem are much more restrictive. So the second theorem assumes less about the orbit, but more about the flow. So there is this implication, but it's not like literally true. So about Reeb pseudo-rotations, the point is that just as for Hamiltonian diffeomorphisms, they can have very interesting dynamics. It's a small class of maps, but it's a narrow class of maps, but they can be extremely interesting. The first examples here, or the main examples here, go back to Katok in 1973, and there are also constructions in dimension 3 of Albers, Geiges, and Zemich. So these are two main results we are going to talk about, and there is also an extra bonus more related to the methods we are going to use. So let's go through it. It has to do with the Reeb barcode entropy, and here we can work with a general Liouville domain. let's take the filtered symplectic homology, non-equivariant of that domain, and think of it as a persistence module. We are going to, as usual, we are going to look at the number of bars greater than epsilon beginning below the period threshold S. Think of it as a function of S, and then look at the exponential growth rate of this function, first for a fixed epsilon and then send epsilon to 0. We get a number, possibly 0, possibly infinity, and call it the epsilon barcode entropy, and then the barcode entropy of that Liouville domain or Reeb flow. It's actually independent of the filling. So there is a theorem of Enderle and Sol in 23, which says that the barcode entropy bounds from below the topological entropy of the flow. In particular, it is finite. And a consequence of the methods we use for proving the previous two theorems is that whenever the flow has a compact hyperbolic invariant set, then the topological entropy of the restriction to this set bounds the barcode entropy from below. So you probably have heard us speaking about similar results for Hamiltonian diffeomorphisms or geodesic flows. So this is the Reeb version of that result. And a consequence of it is that in dimension 3, the barcode entropy is equal to the topological entropy, because in dimension 3, all entropy comes from hyperbolic sets. So this is like a little bonus. Are there any questions about the results? I'm going to discuss them. I'm going to discuss the context now in more detail, but are there any questions? All right, so let's talk about this. First of all, much of what I've said, except the barcode entropy part, is not particularly interesting on you in dimension 3. In dimension 3, one can say much more. Regarding multiplicity, there is a very general conjecture which has almost been proved by now. This is 2 or infinity conjecture, and it states that for every Reeb flow in dimension 3, there are either exactly 2 or infinitely many periodic orbits. And this is totally general and totally unconditional. So it's, in particular, it implies our first theorem in dimension 3 without any condition on the Reeb flow. As for invariant sets in 3D, our second theorem, in fact, follows from Frank's and Calvez-Yoccoz theorem, because the result is, in fact, local. This is not obvious from Calvez-Yoccoz, but a later proof by Franks is local, and he already points it out. Also in 3D, there are related results of Christopher Gardner and Prasad. The statement is that the union of proper closed invariant sets is dense, and this also implies the our theorem B, or at least the proof implies our theorem B. And this is also purely three-dimensional, at least at this stage of our knowledge. This results, our theorems are mainly interested in higher dimensions. So let's talk about the first one. Let's talk about multiplicity. The question is very old. It probably goes back to the beginning of the 20th century. starting with Lyapunov, then in the heroic era of symplectic geometry and dynamics, Moser, Rabinovich, Weinstein, and Eklund, people worked on it. The general conjecture here, it's a pretty cheap conjecture. It's based pretty much on the lack of knowledge rather than real knowledge, is that for any Reeb flow on the standard contact sphere, there are either exactly n simple orbits, and all orbits are elliptic, or infinitely many orbits, and at least one of the orbits is degenerate or not elliptic. So this is like would be the most straightforward generalization of Frank's theorem to Reeb flows, and at this moment it's totally out of reach. Like there is very little there is almost nothing intelligent one can say here without imposing extra conditions. It's instructive to look at what is not known. So if we take an arbitrary Reeb flow on the contact sphere, it's not known if it must have more than one simple closed orbits or more than two in the non-degenerate case. So if we try to go a little bit beyond the Weinstein conjecture, we are getting immediately stuck without any extra assumptions. So I think in the non-degenerate case, we have at least two by an observation of Gurel for the spheres, and in general, there is a result of Brogat and Kong and Maccarini a few years later. So for other manifolds. But this is pretty much everything that is known without the index conditions. On the other hand, if we start making assumptions on the index, namely impose some dynamical type convexity conditions or dynamical convexity conditions, then actually we immediately can say something interesting. So dynamical convexity plus non-degeneracy implies that there are at least n simple uniterated periodic orbits. Without non-degeneracy, we roughly get half of the expected lower bound, namely n over 2. And again, the type of dynamical convexity we use here has been the conditions have been weakened through a series of papers, and now I think these are pretty big index assumptions, but they're still there. Kind of one has to assume something. The key result, the key breakthrough here was by Long and Zhu in 2002. They proved both of these lower bounds for convex spheres, but the argument essentially goes through for dynamically convex flows. This is an observation of Gatt and Kahn. And many other people worked on this type of lower bound. So the upshot of this comments on multiplicity, that if you want to say anything, you need to make an assumption on the indices. There are also some related results on perfect flows, but with inequalities going in the other direction. I think the first one is by Gurel, and there are some other results, but again, relatively little is known here. As for invariant sets in higher dimensions, I think there have been pretty much nothing seem to be known. So there is some related work about invariant sets and invariant measures, but this is mainly enough. For the most important here is, of course, the result by Fish and Hofer, that there are no minimal there are no hypersurfaces with minimal characteristic flows. There are refinements by Prasad. In higher dimensions, there is a work by Prasad on probability measures, and by myself and Nietzsche, that in all dimensions there are no uniquely ergodic hypersurfaces in R2n, but these are results of different type. So essentially, theorem B, I think, is the first of its kind, in spite of all very strong assumptions we need to make in that theorem. As for the Barcode entropy, it's been extensively studied in the last few years, starting with Hamiltonian diffeomorphisms by Cineli and Gurel and myself, for geodesic flows by Gurel, myself, and Mazzucchelli, for F flows, Fenderly and so on, and Fernandez more recently. Some of the proofs are closely related to the categorical entropy, and there are kind of more recently established connections with triangulating persistence modules and etc. So maybe one point I should make here is that this B epsilon, this counting function for bars of lengths greater than epsilon, comes up in other geometric aspects of, or in other geometric applications of barcodes. But I would say an interesting point is that, again, it does come up, but not very frequently, or at least at the moment, it seems to be less universally useful than I expected in the beginning. Nonetheless, it's been studied by Cohensteiner, Edelsbrunner, Mileika, Polterovich, and other people, let's put it this way. So are there any questions about the context? Because our next subject is proofs, and this is a separate story. Questions about the context?
Oh, this restriction of a positive of this positivity assumption on the index is it something that's truly essential, or is it something that maybe if we have a technical breakthrough, you would expect it to be fixable?
So here is the conjecture. The conjecture, of course, involves, in general, at least for this sphere, you expect either n or infinitely many. Sarah, I don't know. As I said, there is no single result which beyond dimension 3 that would not use some kind of index condition. For all I know, this conjecture might be totally wrong. It's mainly based on our lack of knowledge rather than knowledge. I don't think people have seriously tried constructing counterexamples here. I've tried a little bit, but so it's hard to say. If you want, I would say at this point, if you want to prove something, you need to make an index condition. These are relatively weak conditions at the moment. So people pushed it very much to the limit, but they're still there. Other questions? All right, then let's talk about proofs. this is a kind of separate story by itself, and proofs involve two ingredients. The boundary depth upper bound, the crossing energy lower bound, and this is a key new ingredient mainly due to Cineli, and index recurrence. And there is a technical complication here that we cannot really work, for technical reasons, we cannot really work with symplectic homology. We have to work with specific Hamiltonians. And the class of Hamiltonians, which is the most convenient for our purposes, is called semi-admissible Hamiltonians. And these guys look like this. Here is your Liouville domain. So the horizontal axis in this picture is simultaneously the symplectic completion of the Liouville domain. So here is the Liouville domain, and this is the cylindrical part of the Liouville domain, and this is the cylindrical parameter ranging from 1 to infinity. So the class of Hamiltonians we are looking at, they're identically zero in the Liouville domain. Then they are strictly convex up to a certain value of the parameter, which depends on the Hamiltonian, and then it is a linear function of the parameter a r minus b, and we will refer to this a as the slope of the Hamiltonian. The good thing about this class of Hamiltonians that they actually captured the symplectic homology. Namely, the Floer homology of such a Hamiltonian is literally equal to the symplectic homology of the Liouville domain, up to changing slightly the action threshold. So I need to reparameterize the action, and of course the whole thing is bounded from above by the slope of the Hamiltonian. But if I am allowed to increase the slope, then the Floer homology gives me the symplectic homology more or less on the nose. So I don't need to pass to the limit of the Hamiltonians or do any of these tricks people do when defining symplectic homology. So this is the class of Hamiltonians we are going to work with. Are there any questions so far? So the next, now we are ready to get into the ingredients of the proof. So the first one is rather simple. So let's look at the total symplectic homology of the Liouville domain. To distinguish it from the persistence module, I'm going to denote it by SH infinity. So this is the symplectic homology for the full action array. So it's known that the symplectic homology vanishes whenever the Liouville domain is displaceable in its symplectic completion. In essence, this is a theorem of Viterbo from 1999, and then it's been generalized or reproved many times, starting with Chilebak, Frauenfelder, and Oanchi in 2010, then Sugimoto in 2016, etc. So it's something that has been reproved many times in various forms. So another ingredient we will need here is the boundary depth. The longest, the biggest bar in the persistence module. It was introduced by Usher, and in general, useful to keep in mind that the longest bar can actually be infinite in this case. Nonetheless, just because the range of actions here is unbounded from above. So there is a simple observation by Invariant, Sean, and myself that whenever the symplectic homology of a domain vanishes, the boundary depth is bounded from above. So it's finite. And the upper bound is very explicit. One can take the non-equivariant symplectic capacity, or one can take just the displacement energy, which is a slightly weaker lower bound. And when you think, either way, it's a very simple result. So in fact, we need, as I said, we have to work with specific Hamiltonians. So we need a result for a similar result.
Victor,
yeah.
if SH infinity of W is 0, it does not imply that W is displaceable.
No, as far as I know,
because you said you can take the displacement energy.
Oh, yes.
There may be no displacement energy there.
You're right. So
Okay.
if there is no displacement energy, you need to take the first non-equivalent symplectic capacity. And it's always there. So it's always there when the total homology is 0.
Sure. Thank you.
So I'm just thinking of a ball. So. All right, we need a variant of this theorem for specific Hamiltonians, for admissible Hamiltonians, rather than the symplectic homology. And it's slightly more awkward to say because the global Floer homology of an admissible Hamiltonian is non-zero. So there are actually infinite bars. But if I stick to the range of, let's go through it. It illustrates pretty well like how this actual proof goes, what flavor it has, and it's a little bit painful. So let's take an admissible Hamiltonian and let's fix a parameter slightly below the slope of it. So if in this picture we would fix a parameter below this slope. So I denote that parameter by A. So then there exists a constant C, which depends only on age, such that when I look at the iterated Hamiltonians and I look at the all energy levels below Ka, then all bars ending below this level Ka have lengths less than C. So it is, the point is that I don't have an upper bound on all bars, but I have an upper bound on bars ending below a certain threshold, and this threshold goes to infinity along with the Hamiltonian. So I can sort of push it as far as I can. So this, and it's slightly, it takes a bit more effort to prove than the symplectic case, but it's still not a difficult result. So the second ingredient is crossing energy. It has a long story. And basically the idea here is, it goes back to the to an observation by Gurel and myself, that whenever you have a hyperbolic orbit of a Hamiltonian diffeomorphism, or even a locally maximal orbit of a Hamiltonian diffeomorphism, there is a lower bound on the energy of a Floer trajectory, asymptotic to an iterate of this orbit. And this lower bound is independent of the order of iteration. So to reach a locally maximal orbit, you need some energy. And this energy is bounded from below by something totally independent of the order of iteration. So, and this is for Hamiltonian diffeomorphisms. And for Reeb flows, the situation is much more complicated. So let's go through the result in detail. We start with a locally maximal orbit of a Reeb flow. It has period T. We take a semi-admissible Hamiltonian with the slope greater than that period. Then this orbit will register as a one periodic orbit of that Hamiltonian H. It will never be locally maximal. And then I'm going to start iterating the Hamiltonian and look at the iterated orbits. And I'm going to fix an admissible almost complex structure. Then the assertion is, the statement is that under very minor additional requirements on the Hamiltonian, the energy of any Floer trajectory asymptotic to an iterated orbit is bounded away from zero by a constant which is independent of anything, depends only on the initial Hamiltonian and the orbit. And the important point here is that when I start, what makes this difficult is that when I start with a locally maximal orbit of a Reeb flow, it's no longer locally maximal as an orbit of an admissible Hamiltonian. Here is the picture. I have, and here is like the main ingredient of the proof. So in this picture, again, this part is a completion of the Liouville domain. Here below, I have the Liouville domain itself. This is the cylindrical part. This here, I have the iterated orbit. The entire cylinder of this orbit is an invariant set, so it's never isolated. And I'm looking at Floer trajectories which are asymptotic to it. And we claim that the energy of any such trajectory is bounded away from zero by some universal constant, which depends only on Z and H. And the difficulty that comes up here is that when I look at this Floer trajectory, it can get closer and closer to the Liouville domain. If it enters the Liouville domain, then, and it could, then the standard monotonicity result will tell you that it has energy bounded from below. But hypothetically, it could touch the Liouville domain or get very close to the Liouville domain, and the flow here is, the Hamiltonian flow is very sluggish in this area. And I did not tell you what the proof is. The proof actually breaks down. So the key result here, which makes it work, is a theorem of Cineli that actually, when the energy is small, the Floer trajectory is bounded away from the Liouville domain. It never gets close to it, and this bound is depends only on the Hamiltonian and the energy. So
sorry to interrupt
you
again. Sorry to interrupt you again. But so you don't assume that A is not the slope A is not the length of a periodic orbit?
I assume, sorry, I forgot to mention it. I don't want the slope to be in the, actually, in the period spectrum. I don't want the slope to be in the period spectrum. And what happens in this theorem, I'm taking the Hamiltonian, I'm taking the Hamiltonian with the slope greater than the period of Z.
But then I don't understand, why do you say that you have families of periodic, that you have a cylinder of periodic orbit? In that case, it would be isolated, no?
No. I have a cylinder of periodic orbits, but not one periodic orbit.
But even
It's isolated as a one periodic orbit, but not as an invariant set.
Ah, okay. Okay, sorry. Okay.
And so in the crossing energy result, it's very important to have your periodic orbit isolated as an invariant set.
Mm-hmm. Okay. Sorry for that. Yeah.
Mm-hmm. It's a confusing point. So there will be like this whole cylinder here sitting along Z will be filled in by periodic orbits of some period. So this is like this part, the behavior of the Floyd trajectory, the fact that it's stays away from the Liouville domain, this is what was holding us back for many years. It doesn't really follow from any sort of standard maximum principle or anything like that. It's a standalone theorem of Cineli. So the third ingredient is index recurrence. It's a linear algebra statement which is a bit awkward to state. So let's try to do it. So I'm going to focus on the simplest non-degenerate version of index recurrence. Let's take R elements in the universal covering of the linear symplectic group, and I will require the mean indices to be positive. And I want to look how the mean indices change on the iteration. So let's go, how indices, the Convex-Zender indices change on the iterations. Here is the notation. Then it turns out that there is a certain regularity to the behavior. And maybe the simplest way to do it is this. Let's look at the sequence of the indices, and let's look at an arbitrarily long segment in the sequence centered at 0. The index of the 0 iteration is not defined, so I'm going to, so when k is equal to 0, I have here the index of the identity. I'm going to throw it away. So the point is that this arbitrarily long interval will repeat itself infinitely many times in the sequence of all indices. But of course, because the mean index is positive, it will grow. It cannot literally repeat itself. It will repeat itself up to a shift. And moreover, this shift can be taken the same for all linear maps in this finite collection. So in other words, like focusing back again on an individual map, when I look at the derivatives sequence, the difference between successive iterations, any interval in that sequence will repeat itself infinitely many times. So this is the reason why it's called the recurrence. And the event when this repetition happens will be referred to as an index recurrence event. So there is a closely related theorem, the common jump theorem by Long and Zhu from the same paper where they proved the multiplicity result. And the index recurrence can be derived from that theorem or proved directly. And here is the implication of the index recurrence in the dynamically convex case, and this is actually what we need. So there is a sequence of iterations, Kij, where I is the index of our symplectic map, label of our symplectic map, such that all sort of Kij's iterations are some finite distance n-1 from this dj. So they're in this finite, very controlled interval, and this dj is the same for all maps in our collections. And all other iterations are some distance away from it with a little gap of length 2. So these iterations are in that finite range, and everything else is a bit away. So how would we make it more clear? Again, there is maybe let's just keep it like that, and then I have a few more minutes to say how the in general proof works, and I think it will become more clear from that. So let's focus on a version, on a simplified version of theorem A. I'm going to assume non-degeneracy. I'm going to assume dynamical convexity in its full form, and I'm going to work with the symplectic homology rather than the Floer homology. And here is what I want to prove. I have a non-degenerate, dynamically convex Reeb flow in the sphere. I have a hyperbolic closed orbit. And then I claim that there are infinitely many simple closed Reeb orbits, the outline of the proof. So I have the symplectic homology. For every closed Reeb orbits, I'm going to have two generators. One has degree equal to the Conley-Zender index, and the other one has degree the Conley-Zender index +1. And I'm going to have one generator for the interior of the Liouville domain. Arguing by contradiction, let's assume I have finitely many periodic orbits. The first one of them is hyperbolic. Let's look at the actions. And by scaling the contact form, I can assume that the action of the hyperbolic orbit is equal to the mean index. It's just convenient to do so. Let's consider an index recurrence event. I have a sequence of iterations, and I have some index d about which the Conley-Zender indices of iterated orbits are centered. So I will look at the generator which corresponds to the iteration of the hyperbolic orbit. And I claim that this is a non-exact cycle in the symplectic homology complex, and which this will make the symplectic homology non-zero, which is a contradiction. So to see this, I'm going to break down my finitely many orbits into two groups. Those with the same ratio of the mean index and action as for the hyperbolic orbits, and those with different action. And now I'm going to take the index action plane and plot the actions and indices of all orbits on this plane. So there are several regions here. At the very center of this picture, we are going to have the iterated hyperbolic orbit. We have also the iterations coming from the index recurrence event. And depending on which group an orbit belongs to, it will have either the action very close to the action of the hyperbolic orbit. So it will be somewhere in this range with the action very close to it. Or it will be somewhere here with the action very far from the action of the hyperbolic orbit. All other iterated orbits will have indices somewhere here, and they are, and the index difference with the hyperbolic orbit is greater than 2. So because of this region, because on the previous picture of this gap. And so now we look at the Floer differential and how it can connect orbits to the hyperbolic orbit here in the center of the picture. If our iterated orbits are in this range, in this little square, then the action difference is too small. It's smaller than epsilon, and this cannot happen by the crossing energy theory. If the orbit is in this range, then the action difference is large. And this cannot happen because the boundary depth is bounded from above. And if the orbits are in that range, then the index difference is at least 2, and there is no Floer differential. So this orbit is actually closed in the closed and not exact in the Floer complex, and this cannot happen. This is basically the gist of the proof, and this part is relatively simple. I would say the like key new ingredient to the proof. Index recurrence is not new. It's been around for a while. The key new ingredient of the proof is the crossing energy theorem, and this part of the crossing energy theorem by Cineli. And this is like the central step of the argument. There is an analog of the crossing energy of the theorem for locally maximal hyperbolic sets, and this is what is used in the entropy case. Let me stop here. Thank you.
Thank you. Any further questions for Viktor?
Viktor, may I ask you, so what happens in generic case? What is known? So, like, can you prove that there is hyperbolic orbit? Can you prove that there is infinitely many, and so on?
C infinity generic.
Both C infinity, C1, whatever.
I think so. So I'm trying to remember what is known. So for Hamiltonian diffeomorphisms. It's known for a huge class of symplectic manifolds, but not all symplectic manifolds. This is in the most advanced version. This is a theorem of Arita. And basically what you want to do, the argument goes like this. What you want to do, you want to say that there is that Floer's theory tells you something like this. Either you have infinitely many hyperbolic orbits, or you have a non-hyperbolic orbit. And when you have a non-hyperbolic orbit, you can use Birkhoff-Moser-Lewis theorem to create actually infinitely many hyperbolic orbits nearby, or at least to create infinitely many orbits. For Reeb flows, at least for the sphere, it's known that C infinity generically you have infinitely many closed orbit, and the proof is different, I think. So it's known that when you have finitely many closed Reeb orbits, their mean indices must satisfy a certain resonance relation. I think it's been proved several times, starting with Claude. Then I think it was reproved in a slightly more general form by Eli Kerman and myself, and probably like several other people. And so this is like an equality. Roughly speaking, the sum of reciprocals of the mean indices is equal to 1/2. And something like that can be easily destroyed by a small perturbation. Any equality, like you change one orbit and the sum is no longer 1/2. So this is the argument. This is how you prove it for the sphere. It's actually kind of a much neater proof than for symplectic manifolds. What happens for other contact manifolds, I have not thought about it. Again, I'm kind of, in general, not very much in favor of asking questions about contact manifolds in all dimensions, just because you have few tools to work with. So it's probably, but if kind of whatever you can say in general, like it's not particularly interesting. It's kind of things are either totally inaccessible or readily accessible. So I think one can probably say something in general for other manifolds. Under some condition, you need to assume at least that the manifold is fillable, that there is something like symplectic homology. I have not thought about it. But...
Yes,
and C1, it's probably much easier, I think.
I feel very old, and I should feel very old actually for saying that, but in my thesis, I proved that in the CK topology for K at least 3, you have either infinitely many periodic solutions or they are all hyperbolic, and this cannot happen if n is even. And this is by this resonance condition that Viktor mentioned.
But Claude, do you have any assumption about the manifold? Your result is for the sphere. For the sphere, yeah.
It's for star-shaped. It's for star-shaped domain in R2n, which is the case of this.
Other questions?
Well, if not, let's thank Viktor again, and we can
No,
continue.
sorry, I had a question.
Okay.
You seem to say that you don't want to use equivariant homology or equivariant Floer homology for some reason, which is a little bit surprising because usually things get easier to prove if you use the equivariant one.
No. I did not say I don't. I did not.
I could change
no,
I could change the question.
Not say it. I did not
Can you
say
improve the result by using equivariant Floer homology? That's another way to put the same question. You see, you have this bifurcation of one orbit that becomes two critical points and so on, which of course you don't have if you use the equivariant case. And
so,
or have you tried and where is I pointed? I don't know. I mean,
so I don't think things will become easier. One thing that so when we try to translate this proof to the equivariant version, I don't think things will become easier. The index recurrence is
no, that's a thing. That doesn't.
Yeah, that's a linear algebra. It's a statement. So the crossing energy will probably hold. The boundary depths upper bound will, as stated, will definitely break down. When you look at the equivariant homology as a persistence module, say positive equivariant symplectic homology, you get infinitely many. First of all, you get infinite bars. Okay, no, I'm not saying it right. Here is, let's look at the equivariant symplectic homology. Not positive, but the total range from 0 to infinity as a persistence module. It's still 0. The global homology is still 0 by the spectral sequence. But I don't think in general, or at least I don't know if in general the boundary depth is bounded. When you look at what happens for the ellipsoids, then it is actually, I think, unbounded. Or maybe it is for the ellipsoids, it's bound. No,
it depends if you take H with a fixed slope, and I mean it dies in a different way somehow, the equivariant, non-equivariant.
Yeah, but I would say this part of the picture becomes more complicated.
It's more okay. So that's okay. That's the answer.
So one can probably reprove the theorem using the equivariant symplectic.
No, there's no point in doing that.
Yeah. But it's not worth the trouble.
Okay.
At least if you want to reprove it, it's not worth the trouble.
No.
This is the answer. Actually, I think it's an interesting question. What the barcode in what the equivariant persistence module in this case looks like. One can sort of trying to understand it beyond ellipsoids.
No, I think the point will generate K of U, where U is the degree 2 generator, and then they get killed. The powers of U get killed.
They're going to get killed farther and farther.
One after the other. I think that's what happened. That's the difference with the non-equivariant case. But no, if you say it's not worth the trouble, there's no point.
Well, I think it's not worth the trouble for this proof, but in general, it's an interesting question. Like, It's an interesting question to understand how this persistence module behaves in general, actually both equivariant and non-equivariant.
I agree.
So one can do it in the integrable case for what are they called? Toric domains, but beyond that, it gets totally incomprehensible.
Okay, thanks.
So I guess at this point, let's thank Viktor again for this wonderful talk.